This video is a follow-up on the previous video concerning the sign file tree program written Cython Plus, which, given a directory, scans all the files in the directory and its subdirectories, collects metadata for every file or symbolic link or directory, and computes a hash digest for every file based on the contents, with the idea to have a way to sign a file system to detect tampering at boot time, so as a secure boot strategy. This is all explained in the previous video, and we're still in the same Python virtual environment with Cython Plus, and the Cython Plus standard library is already installed. And we're actually still in the same folder where we compiled the sign file tree program. So we can run this program again. It's here, it's compiled. So what we can do is run it from Python like this, and we can here give an argument for the path. By default, it will take the current path, but let's take the root folder, which has a bit more files, and let's start by let's redirect the output to some result JSON output, so as to avoid polluting the terminal screen. And let's just try this for one thing. Oops, I forgot the end quote. So this goes relatively fast. Can time it. So this is a good way to look at it, because it's it happens that the root folder is small enough that it doesn't take too long. It's not full of many gigabytes of files, but it's also long enough that it can actually see some results. So what we're going to do is we're going to use task set to set the number of processors assigned to the problem. So if we take one processor, the processor 0, and launch it, you can expect this to take a bit longer. It takes 8 seconds, and the real time and the user time pretty much the same, because there's no parallelism involved. Now if we double the number of processors involved, so 0 and 1, we see that the total user time involved is still 8, but the real time almost got halved to 4.5. So it's not fully halved, but it's the kind of results we would hope and expect to see. It's going almost twice as fast. Let's continue this trend 4 times. So processors 0 to 3, same trend. Let's go to 8 processors. Again, same trend, but we begin to notice that it's not exactly divided by 4 and 2 and 8. It's a bit slower than an 8. So if it was truly 8 times as fast, it would take more like 1 second. So there's some overhead, but not much. It scales pretty well. You'll notice that the full time for the computation stays close to 8. So this is good. Means the overheads on the full time is not too bad. If we go to 16, there we're starting to notice some actual overhead. So the time got a bit better, the real time, the actual time elapsed, but a lot of that was lost in overhead because the user time jumped to 14. And if we go inward further, say to 32 processors, so well, probably depends a bit on runs as well. But we see that the overall user time still jumped up from 8, and the real time got reduced, but again, not as much as we might have hoped. Let's run it a few times to see if this trend looks coherent. Yes. And then we can go to the full 47 processors on this machine. And we see again the kind of results we had at the very beginning when we didn't use task set. So we get some increase in speed again, and we're faster than we were with only 8 processors, but not so fast, so much faster as we could hope from the trend from 1 processor to 8 processors. So here we almost got a halving of the time all the time, and from 8 processors to 48 processors, we only managed to essentially divide the real time by 2, and a lot is lost in other costs, overhead, something. But this is not fully unexpected. The program does 2 main things. It hashes files and it reads files. So it does a lot of I/O, disk I/O, and it does a lot of CPU intensive computations to run the hash algorithm. And we can hope to parallelize the CPU computations across multiple cores, but at some point the bottleneck will become the disk I/O, and so no matter how much we parallelize, we still need to have the time to read the files, and this is a property of the system, so not much we can do about it. But we see that the program scales pretty well. Let's compare it to an equivalent program within Python. So I have a new branch on this Git repository called Python. Oh, I was already on Python. Well, okay. So I already have the Python Python file main.py, which isn't what was used so far when I import main, because it's used in priority the compiled C extension module from Cython Plus. So to use the main.py actual Python file, I will need to refer to it explicitly. But first, let's take a look at how it's done. So what we do is we use the multiprocessing module to share the work across multiple cores. And we need to use multiprocessing, so we have multiple processes instead of multiple threads, because of the Python GIL. So essentially we have a Python interpreter per process, and we create a pool of processes and a convenience scheduler class to give work to some pool somewhere. So this is just a pool of processes. The fact that they are separate processes means we cannot share memory as easily as in Cython Plus. They're not in the same process. So this means that when we submit work on a new process in the pool, the arguments are essentially fully copied. It's not passing a reference to some data somewhere in the computer. It's fully copying the full contents somewhere else for the new process to use. So this is one source of of inefficiency compared to Cython Plus with the multiprocessing approach. If we didn't use multiprocessing, if we used multiple threads, we would be able to share memory, but then we would be throttled by the global interpreter lock. So we'd still have the same problem. Instead of costs related to having multiple processes and sharing data between processes, which involves the system, we would have costs related to contention on the global interpreter lock. Then we have, well, I won't go into details, but stuff that somewhat similar to the Cython Plus program. I kind of modeled it after the same design. So we have a node class for each kind of node. But the difference here is that we cannot as easily, or actually in any really practical way, dispatch the work for each entry in a directory to another process, so actually parallel, because that would involve copying data that is harder to copy. So if we wanted to call this build node method asynchronously on another process, we would need to copy the node itself and defeat the point. And so we cannot use exactly the same design as the Cython Plus program. So what we're doing is we're just scanning the directories recursively. So this is actually a synchronous call, and we're just building a tree of node, dir nodes, file nodes, symlink node objects that matches the tree of the file system synchronously. And the only thing that we're doing asynchronously is when we're building the file node, we're submitting the work of actually computing the hashes to another process. And we will then later get the result once all the processes have finished running and there is no more file hash to be computed. So this is a bit less parallel than the Cython Plus program, but that is a limitation of the concurrency tools that are available in Python. And copying more data to share across the processes would be possible, but more costly again. And data wouldn't be shared. So if the goal is to later on collect all the data back together, well, we're kind of stuck anyway. So this is this is still a good comparison, because the biggest, as I mentioned earlier, thing the program does is compute the hashes, and that is what we actually really want to parallelize and do AO. And the AO is less parallelizable anyway. The system will be the bottleneck. So the design is otherwise pretty much the same, and then we dump the JSON output. So let's take this program and run it with Python. So if I do it this way, I'm specifically referred to main.py. Actually, I can just do this. So this way, I'm sure I'm running the Python version of this program and not the Cython Plus version, which I was up to now. And the Python version takes an argument for the path to use. Again, by default, it's the current path, but to do the same thing, let's take the root, and let's redirect it also in result.json to avoid spamming the terminal. And let's try this. So this works. We can time it. And we notice straight away that takes a bit more time. So this is the full processor version. Takes a bit more time, real time and user time overall, to process these results. The user time overall is not so much worse. It's 18 instead of, we had something around 8, but it's less than 3 times as much, so it's still acceptable. The system time is much, much higher. This is because of all the interactions between processes and sending data back and forth and all that, due to the multiprocessing approach. And the real time, full on with all processes, is 5 seconds instead of around half a second we had earlier, so almost 10 times as much. So not so good as the first version. But let's try it now with only one processor and see what's going on. So with processor 0, and we launch this program, you can expect it to take at least 21 seconds, which is the user time and system time we had. Maybe less, because the system time could be lower. Exactly. So the system time is not as high because we have less processor interactions. We'll still have some because we're still using a multiprocessing approach, just only has one process. And yes, we have less overhead. So take 14 seconds, 1 second system time, so around 15 seconds overall. So with one processor, we're 3 times slower than with 48 processors. But let's go to 2 processors, and let's see if we double the time. And we do pretty much. So have the same trend, just higher values than we had with the Cython Plus program. Sorry, I meant if we have the time, so if we double the speed. Now let's go to 4 processors and see if the thread continues. Not as much as with the Cython Plus version. And let's go to 8 processors and see what's going on. Yeah, so essentially, with 4 processors, we failed to divide the work by 4, the time by 4. And with 8 processors, we only managed to divide it by roughly 3. So between 3 and 4. So this is pretty much the same times we get as with all the processors. So if I continue the trend, I don't expect to see much change. So adding processors at this stage doesn't improve things like with same as with Cython Plus. But it doesn't even improve the real time. With Cython Plus, we still saw improvements, just it stopped halving the time. With Python, it won't get better than this. So what we see is that the Python program scales much worse than the Cython Plus program. Essentially, it only scales to 4 processors, and then we reach pretty much the peak performance we'll get. Whereas the Cython Plus program scales almost linearly, not quite, but almost linearly to 8 processors, and keeps scaling up when we add processors, just slower, because I/O becomes a bottleneck, probably. Yeah, so the Python version is less scalable than the Cython Plus version, which is not really surprising because of the multiprocessor approach. And yeah, the fact that we have more overhead between processors, and the Python code that does run runs slower as well due to Python's interpreted nature. So yeah, this is interesting because it shows a comparison between performances we can get with Cython Plus program and a Python program doing the same thing with similar designs and a balance of I/O boundedness and CPU boundedness, so balance of I/O and CPU intensive work. That's it.